Scenario with known endpoints. When I say known or unknown endpoints, it's from the leaf perspective, more specifically the ingress leaf perspective. Do we have any knowledge about the destination? Do we know where the destination is in the fabric? In this scenario, we have known endpoints, so the ingress leaf will have this knowledge. So our first host sends a packet to leaf 1. Leaf 1 receives the packet, and from the port and the encapsulation from which the packet is being received, we can derive the EPG and the bridge domain to which this packet belongs. Based on the knowledge the ingress leaf has about the destination, it will know that it needs to send the packet to leaf 3 and 4 where the destination host resides. As such, it will encapsulate the packet and send it over the fabric with the 3 outer headers that you would see there, where the kube database will not be hitting any entry, and as such, the packet will be dropped on the spine. This means that for silent hosts in a network, it's advised to go rather for flooding option, where you can ensure that the traffic will be received. Now, let's say that the spine has the knowledge and we have a kube hit now on the spine side. The spine will know, on top of knowing the destination MAC, it will know where this destination MAC is connected, leaf 3 and 4. As such, it will rewrite the layer 3 header and send the traffic towards the correct set of leaf. As before, the egress leaf will encapsulate the traffic and it will be received by the host. Alright. Couple of CLI again. This is just for the kube lookup on the spine. If you're wondering if kube has any knowledge about an endpoint, specifically in layer 2 side, this is the kind of command you can use. The 2 values that you need to specify are the bridge domain VNet, so it's an identifier for the bridge domain, and the MAC address that you are targeting, of course. Alright, this concludes the layer 2 section, so we are now moving to the layer 3 forwarding section. For the layer 3 forwarding section, topology will be exactly the same, just the hosts are going to change. So we are still redundant over VPC, but this time they are in 2 different layer 2 domain while staying in the same VRF. We are not going to do inter-VRF routing here in the scope of this presentation. From a configuration perspective, if you want the traffic to be routed in the bridge domain, you need to enable the unicast routing flag and to configure a bridge domain subnet under your bridge domain. And once done, we are good to go. Let's take the fabric as before. So this time we are starting with the unknown endpoint. I'm not going to cover the known endpoint scenario for layer 3, simply because it's very similar to what we saw for layer 2. It's actually exactly the same. Instead of doing MAC lookup, we will be doing IP lookup in the endpoint table, but the rest is exactly as is. So let's move forward with the unknown endpoint scenario. Again, our ingress leaf don't know the destination IP. As such, what can we do? Query the kube database. Okay, so we query the kube database, this time for an IPv4 address, so the TAP IP will change. It's not the Anycast MAC, it will be the Anycast v4. And again, 2 possible answers. Does the kube database know the destination IP or not? If it knows it, easy, it will rewrite the destination IP and send the traffic toward the destination host. Traffic will be decapped and received by the handlers. It's a win. If we don't have any entry, what we are going to do is to punt the packet to the CPU of the spine. The reason for that is that we need to generate a more intelligent packet from the spine that needs the CPU power for it. So packet goes to the CPU, and in reply to that, the CPU will send the packet to all the leaf switch in the fabric that we call the special ACI clean packet. This packet looks as follows, so with a given multicast address of 239.255.255.240, which will always be the case, except if you are using the system global GPO. Not very commonly used, but we already saw it. The original packet will be also included in this with a special header type. So if you see an header type matching FFF2, don't be scared, it's just ACI doing its things. Upon reception of these packets on the leaf switch side, again punting to the CPU, and the leaf switch CPU will forge now an ARP request for the destination IP, stating who has this IP, please tell the ACI gateway. Expectation is that the host owning the IP will reply, and now the endpoint will be learned in the fabric, and we will fall back to the scenario where we have endpoint known in kube database and traffic redirected directly to the egress leaf switch. Alright, from a CLI perspective, so we are on the ingress leaf side, on leaf 1. We try to see if we know the destination in the endpoint table. It's a miss. The fallback mechanism will be the routing table. So we check in the routing table, and in the routing table we can see that we are now hitting the bridge domain subnet configured to the UI or API. And we see the next step is the IP. Expectation is that it should point to the spine. How can we verify that? I still use the same mechanism. Log into a spine, check the routing table, where does it lead me? Checking on the spine routing table, we can see that it's a loopback, a local loopback, and this local loopback is actually our Anycast v4 loopback, so that's a win. For the kube database on the spine, this is the command to query for an IP this time. Again, the key will be the VNet of the VRF this time, as we are in layer 3, not in layer 2 anymore, and of course the destination IP that we are looking for. Alright, let's move to the policy enforcement. So now we have the logic in mind on how the forwarding is expected to go over the fabric, but we still want to ensure that the traffic that is going over the fabric is allowed to go over the fabric. The way we do this in ACI is through contract configuration, and the question is, when do we actually need a contract? Contracts are needed anytime we have inter-EPG communication. So when you are having discussions in between hosts inside a given EPG, you're safe to go on a contract needed by default. If now you want two different EPG to have communication, you will need to go for a contract. An example of contract configuration, very dummy one, where you create on the first tab your contract, then a subject which is the children object of the contract, in which you are going to define your filters. The filters will be really the filters as you may expect it, so TCP port 80, TCP port 443, or default allowing anything. Once the contract is created, we still need to associate it with our EPG on providing a contract and consuming a contract. Typically, we would think of this as one of my endpoint group is actually providing some services, and I have another set of endpoint group that needs to consume this service. It could be HTTPS or simply any. Okay, so we know when to apply a contract. Now the question is how to apply a contract. What do we need to actually apply a contract from a leaf switch perspective? To apply a contract, we need three values. The two first ones are the source EPG and the VRF. Based on the previous cases that we saw, forwarding scenario that we saw, those two values, we will already know them when we receive the packet, because based on the port and encapsulation, we are able to derive the source EPG, the source bridge domain, and the VRF. So those two values, easy win. The third one is the destination EPG. This one can be a bit more challenging, and we will see this in later slides. Note that when I state source EPG, destination EPG, I'm actually referring to a specific value that has been allocated for those EPG, which is called PC tag or S class, depending on where you look. So if you already saw PC tag or S class, now you know that it's actually referring to a specific EPG. Alright, so as I mentioned, the two first values are an easy win usually. So typically, if we look at for the directly connected endpoint, what we see is that we have the VRF VNet immediately available there, as well as the S-class value, which is the PC tag, so this identifies uniquely our source EPG. So the two first values, source EPG and VRF VNet, we have them perfect. Now, retrieving the destination EPG itself can be easy. It can be easy if the ingress leaf switch has the knowledge about this this destination endpoint. So in our scenario, 192.168.20.21 is something we know as being a remote endpoint, and if we check it, we see as well the S-class associated with this endpoint, meaning that we know which EPG it is, and we can apply the contract directly on the leaf. But it's not always the case, unfortunately. So in case we don't know the endpoint, this information will be missing. And as such, we need still to somehow check if the traffic is allowed or not. We cannot just drop like that. So what can we do? We will actually rely on the egress side of the fabric. So we will allow the traffic to go all over the fabric without being checked. And on the egress point of the fabric, we will say, you need to check or drop. The way we do it, so ingress leaf switch receives the traffic, determines the two initial values, source EPG and VRF. When it sends the packet towards the fabric, If we zoom into the VXLAN header this time, we will see that the VXLAN header contains the VINID, which should identify the VRF. It contains as well the source class, which is the information about the source EPG, and it has the policy applied bits. Those policy applied bits would be set to 0, and this means that upon the reception of such packets, the egress leaf switch 4 needs to apply the contract. It can do it quite easily, as the two first value in the VXLAN header are the two value it needs to apply the contract, and the third one is an information about the locally connected endpoint. So then in the EPM table on leaf 4, we expect to see the connected endpoint, and we should see the destination class available, so destination EPG PC tag. In terms of CLI lookup, what can we do? So here, this just show you how to get the PC tag value for some EPGs. There are easiest way, typically going, if you're familiar with the UI, you just go to your EPG in the UI and you would see the S-class or PC tag information there in the configuration of the EPG. But the main key point is to have those S-class, and then if we want to check if we have a contract program on the leaf switch side, we can check what we call the zoning rule, which is the implementation of contracts on leaf switch side. So the command that you would type is show zoning rule, source EPG, you specify your source EPG, and destination EPG. The scope is actually identifying the VRF. If you want, so here in this scenario, we can see that in between our source EPG and destination EPG, we have a contract named minibar demo with a permit action that is being applied. And this contract applied a filter default. If you want to understand what this filter default is, there is a command that allows us to check the zoning filter. Here, for example, we can see that it's allowing header type unspecified, meaning any kind of traffic to go through. And that's already concludes today's session.